Hi, we're going to be going over Chem 102, Chapter 12, and we're going to go through the first couple of sections in this video. So here's a list of all the topics that we'll be covering in Chapter 12. And the first section is pretty short, just as a kind of reminder of intermolecular forces. And so these are some things that you may have seen in Chem 101. Basically, intermolecular forces are attractive forces that hold the particles together in their condensed phases. So condensed phases are just like the smallest amount of space between particles. We know that gases have a lot of space between them, so even if they're condensed, we are looking at more space in between them. Liquid has less space in between than gases, but is more fluid, less structured, and solids are very structured. We're going to be focusing on liquids and solids in this chapter. So we can imagine that solid intermolecular forces are maybe stronger than liquids or gases because they're more closely packed together, versus gases intermolecular forces might be a little weaker because they don't really interact with each other as much. And you might have learned last semester that gases, we just consider their intermolecular forces actually to be non-existent. And that's not necessarily true in real life, but for ideal gases, so we can use all those math equations you learned, we do have that. So in section 12.2, we're talking about liquids. And the first thing we're going to talk about is the surface tension. So surface tension is basically like how much energy do you have to put in to increase the surface area of a liquid. So the stronger the surface tension, the stronger the intermolecular forces, the tighter the particles are held together, the higher that surface tension. So you can see a picture here of some water beating on like the door handle of a vehicle, it looks like. And that beating is a result of surface tension for water. Water has hydrogen bonding, which is pretty strong intermolecular forces. And so for its it's like with its mass, its density, a lot of its different characteristics, it has a pretty high surface tension. So it takes a lot of energy to push to move the particles around to increase that surface area. So like things can float on top of water if they're particularly light. There are bugs that exist that have specialized feet to be able to stride atop water. And surface tension also applies for the intermolecular forces inside of the liquid are similar. It's just on the surface that we talk about surface tension. You're probably familiar with surface tension, so I won't say much more about that. But basically, you want to make sure that it's stronger intermolecular forces, more surface tension. Um, Similar to surface tension is capillary action. It's based off of um, the ability of a substance to adhere to other substances and then have cohesion between themselves. So in this case, we have a graduated cylinder. You may have noticed that when you read a graduated cylinder, it has this little meniscus, and we always read at the bottom of that meniscus, but you see the water go up on the edges. The water is adhering to the glass. So it's having this adhesive property effect. Now, if you were to put something like mercury in a graduated cylinder, you would see it didn't have that adhesion. And so in this case, we're looking at cohesion. So attraction between the particles is greater than the attraction between the glass and here. But then the attraction for water to have cohesive forces is less than the adhesive forces for this glass. So water is actually attracted to the glass a lot, and that is why it causes that little upward shape. And so because of these actions, you will have capillary action, which is like if you have a small little tube or a straw and you put it into liquid, the liquid can travel up a narrow tube. Really, we talk about it more, and you'll use it in organic chemistry, capillary tubes. They're really, really tiny tubes. You don't have to actually put any pressure or suck liquid up. You just put the tube in the liquid and the liquid will go up into the tube, which is interesting and cool. Viscosity is a measure of the fluid's resistance to flow. So if it's more viscous, it's not going to flow very well. Usually, if you have really high intermolecular forces, you'll have higher viscosity. So, for example, glycerol has a really high viscosity, but look at how it has all this hydrogen bonding on it. And so that makes sense that it has really strong intermolecular forces and therefore a higher viscosity. We're going to be focusing a lot of this section on vapor pressure. So vapor pressure is also something that's dependent on intermolecular forces. When you have the surface of a liquid, some particles can go into the gas phase, even if it's a liquid at room temperature. So if you have a bottle of water in front of you right now, some of that water is turning into water vapor or gas, right? At the temperature that we're at. It's just like a process that happens because not all particles have the same amount of energy. So we have our kinetic energy, or E sub k, and when we have a sample at a certain temperature, most of the particles would have a certain kinetic energy, but a small number of particles would have a high kinetic energy. And temperature is related to the average kinetic energy, so it's not necessarily like the individual pieces. Sometimes individual water molecules just have a lot of energy and they can fly out and become gas. The pressure of that gas, that vapor that's produced, is the vapor pressure. So as we increase the temperature, so let's say we have a lower temperature, so more particles have a lower kinetic energy. So the number of particles that can escape as a gas is smaller. Let's say this is the energy you need to escape as a gas. If you increase the temperature, we have most of the particles are, at a little bit of a higher kinetic energy, but we're spreading out the number of particles, and more of them are now going to have energy to escape. So that makes sense. Is if you increase temperature, then you can get more of your liquid particles to become gas because they have more energy. The more particles that become gas, the higher the pressure that gas puts on the container, the higher the vapor pressure. And you know this, like increasing temperature, increasing pressure is similar if you just have all gases, but in this case, we're actually creating more gas, and so it's more of a increase in number of moles, increasing pressure situation. So kind of putting to pictures what I was mentioning about what the vapor pressure really is. So there's really this two-way street between, so back and forth arrow between liquid and gas at the surface of any liquid that can go into a gas. The vapor pressure, if you just throw a liquid into a container, vapor pressure is going to increase until we get this what's called equilibrium, where we're kind of have the rate forward and rate reverse is the same. We call that dynamic equilibrium, meaning we're still having processes happen, but we're not really changing the amount of either thing. So we have evaporation happening and then condensation happening at the same rate. So thinking through this, so we have a liquid, it's frozen at this point, we let it heat up, it turns into a liquid. When it turns into a liquid, we're going to have some particles that are going to be gas because some particles at any given temperature will have enough energy to jump out. They are going to put pressure on the container, which means on in this little tube here. So we're going to be pushing the mercury in this tube up a little bit. So the height difference between where we started and where we have now is going to be related to the vapor pressure. So we can actually measure that height difference in millimeters of mercury or something like that. Now, if I start to increase the temperature, we'll see we can make more gas particles. And so my vapor pressure increases. Still at a liquid, normally at this temperature, I'm still a liquid. I haven't reached boiling point yet, but because I have more energy, more particles are going to be able to jump out as gas. And then I guess this one is showing, it looks, so these two are the same as once we reach a certain equilibrium, we see that there's no longer any change in the difference in the pressure. but we still have particles going back and forth between liquid and gas. So we've reached equilibrium at this point because we see C and D, the vapor pressure hasn't changed anymore. It now is in this state where it's just going to stay the same as long as we're at the same temperature. So the first process, oh, hold on, this is talking about just a graphical representation of this. So vapor pressure starts off at 0, it increases until it stops changing. That's that rate of evaporation versus rate of condensation. So we look at a graph here of rate versus time. So if we start, our rate of condensation, so condensation is gas to liquid, is very low because we don't have any gas. And then rate of evaporation stays about the same. So if we have liquid, it's going to turn into gas and it stays about the same. Now the rate at which we're turning gas back into liquid is going to increase the more gas we make. So the more gas we make, the faster it can turn into liquid. And then we get to a point where if one turns into gas, another turns into liquid, and we have a rate that's the same for both processes. We'll talk a little bit more about this in class, and hopefully it will make a little more sense. Vapor pressure increases with temperature because as we increase the temperature, we can get more particles into the vapor phase. And so you'll see the vapor pressure of 3 different things, and you can see it as the temperature increases, the vapor pressure increases, and it gets to a certain point where you reach like a certain breaking point where your vapor pressure just shoots up. And I wonder if you can tell what that is. So for water, what happens at 100 degrees Celsius? Just think about it. And so that would maybe be a reason for why we just kind of shoot straight up, because there's something happening there at 100 degrees Celsius. So we can assume that if this is the point for water, that we can assume this number is the same point for diethyl ether and this number is the same point for mercury. And notice that when we reach that point, the vapor pressure is a certain pressure, and that pressure is 1 atm. So just think about kind of what that means, and we'll talk about it in a second. So what I'm hoping that you're noticing here is that the boiling point temperature is related to the vapor pressure when the vapor pressure is equal to the atmospheric pressure. So boiling point temperature, maybe not temperature, so the boiling point is when the vapor pressure, we can say P vapor, P vap, is equal to the atmospheric pressure, P atm. So when the atmospheric pressure of 1 atm happens, and the vapor pressure are the same, so my vapor pressure is the line, right? Or the vapor pressure is this right here, but when the vapor pressure of the line hits 1, that's when we have our boiling point. The boiling point is the temperature you're at when vapor pressure equals atmospheric pressure. We'll talk in class a little bit more about, why that is. So we have some nice fun equations, and you may not think that they're fun, but they are extremely fun. On your equation sheet, please make note of any changes that you see. So on the equation sheet that you've been handed in class, you might see differences. We are fixing them. I just may not have printouts for you as quickly as possible. And hopefully if you're watching this video later than I made it, you won't have to worry about this. But just check it to make sure. So in the back of your equation sheet, you should see these equations I'm about to show you. Just check to make sure that they're the same as what's in the slides. The Clausius-Clapeyron equation relates the natural log of the vapor pressure, which is P, to the enthalpy for vaporization. So that's the molar heat of vaporization. So basically, like, how much energy do you have to put in to change a liquid to a gas? That's to boil it essentially. And it's inversely related to the temperature there. And then there's an R, that's a gas constant, and then we're going to use this constant. Notice that it has joules because we're talking about energy for the enthalpy. And then C is just an experiment, a determined constant experimentally. So you'd have to look up like for that specific thing what your C is. But with that, we can do a really fun thing. We can make a graph. So the natural log of the vapor pressure and the inverse of temperature being your X and Y. If you plot natural log of vapor pressure versus 1 over T in Kelvin, the slope would be this. So what we're looking at here is Y equals M X plus B. And let me rewrite it so that it looks a little more like that. So Y equals M X plus B. The natural log of P is equal to negative delta H VAP over R. And then my X is 1 over T. And then my B is whatever that constant C is. So the slope, if you plot natural log of vapor pressure against 1 over T as your X in Kelvin, your slope is negative delta H over R. So you could figure out what the enthalpy of vaporization is if you just collect pressure and temperature data for a certain process. We could plot it. And so you can plot 2 points, take your rise over your run. That number is equal to negative HVAP over R. You can solve for HVAP because you know R is a constant. And then if you want to think about how does temperature change vapor pressure exactly, we have this version of the equation. And so we have a 2-point form, and this is helpful for like before and after situations or changes. This is also on your equation sheet. Make sure that there's not a plus sign in between these two terms. It's just straight in, so multiplication. And I've talked about this before, but boiling point is the temperature which the vapor pressure equals the external atmospheric pressure. I want to tell you about a term, normal. If I say normal boiling point means boiling point at 1 atm or 760 millimeters of mercury or 760 torr or 14 psi, whatever you're measuring your normal atmospheric pressure. So normal boiling point is the boiling point at atmospheric pressure. So maybe I should write that word exactly. So boiling point at atmospheric pressure. So if we have a question that says like, hey, what's the normal boiling point? What I'm asking for is if the pressure is 1 atmosphere or 760 millimeters of mercury or 760 torr, what's the temperature? And this is the temperature. The boiling point is the temperature. Oops. Um, and so the boiling point varies with external pressure because you have something pressing down, keeping your substances from turning into gases. And if you get to the point where your vapor pressure equals your boiling point, then you're free to totally evaporate, to totally boil. And that depends on the intermolecular forces and the external pressure. So let's use this equation. So here is a worked example. I'm going to put it at the bottom here, so hopefully you can see that. Diethyl ether, I'm giving you the vapor pressure of it at the certain temperature. I'm giving you the heat of vaporization. I want to know what is the vapor pressure at 32 C. So pause it, try it, and come back. So hopefully you did a little bit of trying, at least just try to set it up, at least just try to throw it into the formula. We're going to use this formula. It doesn't matter what we choose as T1, T2, as long as the T's and P's match. So if we have T1, we're going to take that T1 as 18, and we have to turn that into Kelvin. Why do we have to turn it to Kelvin? Because R is 8.314 joules. If on the front of your equation sheet, it should be, yeah, gas constant is 8.314 joules over mole Kelvin. It's in the bottom right under the periodic table there. So I have to match those units, right? I have to have Kelvin. I gotta have joules. So we gotta change to Kelvin. So this is my T1, 18. That used to be 18 degrees C. And my T2 used to be 32 degrees C. And I just used the formula. Kelvin is equal to Celsius plus 273.15, which is also on your equation sheet. Molar heat of vaporization, I gave it to you in kilojoules per mole. We got to have it in joules because that's the unit of R. So just do a quick conversion there. And then to get out of ln x, if we wanted to solve for ln, we want to calculate the vapor pressure, so we really got to get out of that ln. Remember, to get out of ln, we raise everybody to the E. So maybe that helps you. So pause now and keep going if you didn't finish it before. The rest is algebra. So once you plug in your variables, the rest is just algebra. So here's what the algebra looks like. So they did the whole right side first, got a number. And then to get rid of the ln, we raised both sides to the E. So what's kind of missing here, I think, is ln P1 over P2, and raising both sides to the E gets rid of the ln. And then we just calculate E to the whatever, and that gives you your fraction, P1 over P2. We know our P2, they told us 401 millimeters of mercury. Oh, you know what they did? They reversed it. Why did they do that? So what I would have done is I would have, oh no, I see. They rearranged it first. They rearranged the P1 over P2 is equal to the 0.61, and then they plugged in the 401. You can do it either way. I might have said like 401 over X equals 0.6109. And that's going to give you the same thing though. And then that'll give you the pressure that you're looking for. So it can seem really daunting. Just take it step by step and remember the algebra that you know and love, hopefully, it also applies to this.